This presentation is delivered by the Stanford Center for Professional Development.
All right, we'll get started. I guess we'll announce probably by Thursday when the actual sort of preliminary project proposal is due. You should be thinking about projects, and you probably shouldn't have completed it by now, but you should certainly have thought about it a fair amount and tossed around some ideas. And you should probably be in communication with us if you're not, just to get a little bit of feedback on what you're doing. And we'll probably make this preliminary project proposal due maybe early next week or something like that. And before we make it due, we will put something on the web, or we'll announce something that's going to be very specific as to the format, because it should be like 2 pages, and I think we might just sort of iterate on that. We'll just reject it until it's clear enough for us, clear and simple. So that's what we're going to do. So okay, so let me continue on the material on stochastic programming. So this is going to be one of the examples for stochastic subgradient. So stochastic programming is by the way, it's a huge field. You could teach an entire course on it. There are multiple books on this one topic. And a stochastic programming problem looks like this. You have an objective and constraints that depend on some random variable. And in fact, this can, any actual optimization problem, any one that actually is for some application, is going to look like this to some extent no matter what. Period. In other words, that any number in the data in your problem will trace back to something which is not going to be known that well. So in stochastic programming, you assume a probability distribution on these unknown parameters, and you minimize an expected value, and the constraints are on expected values. Now, expected value might not be what you care about. You might care about things like the variance and things like that. Actually, that's going to be also handled in the same way. You'll see how in just a minute. So the exact same formulation. And so don't think it just means if one of these is if that's a cost, that's the expected cost. If you actually care about the variance of the cost, we'll see immediately that this can be incorporated into a framework like this. Okay. Now, an expectation, of course, is something like an integral. And obviously, an integral of convex functions is convex. So this preserves convexity. So these are convex. That's a convex function. So this. In fact, I should say something a little bit more. When you integrate like this, generally speaking, these expected values, it depends on the distribution on omega, of course. But if that distribution is sort of continuous, or for that matter, it has a distribution that's analytic or something like this, these things actually inherit. They become much smoother. So even if f0 or fi is piecewise linear, for example, or non-differentiable, these are often quite smooth, right? So that's not relevant. Doesn't mean you can use Newton's method because, well, you can't calculate any of these numbers except in very special cases. Okay. Now, one sort of very obvious thing to do is to ignore the uncertainty. And you ignore the uncertainty by simply taking for this parameter value its expected value. And that gives you this problem here. That's the, some people call this the certainty equivalent problem. And I've heard, although I don't quite understand it, other people refer to this as the mean field problem. Don't ask me where that comes from or something like that. It has something to do with statistical mechanics and machine learning and stuff like that. But anyway, so this is the certainty equivalent problem. And what it means is you simply replace this parameter with its expected value and you solve this problem. Now, by Jensen's inequality, this is actually favorable compared to that. So when you solve this problem, you will actually get a lower bound on the optimal value of this one. Okay, so that's actually, In fact, that's the way I remember Jensen's inequality. Jensen's inequality says for a convex problem, variation messes you up, right? Which makes perfect sense. If something curves upward and you vary around something, when it goes down and it can go up. But the positive curvature says that on average you get messed up, which is to say the average cost goes up. Okay, so this is the certainty. And by the way, this is when you're solving, if you do anything involving stochastic programming, you should solve this immediately. And then this gives you a lower bound. Okay, so now, it's not, of course, the solution to this when you calculate the x for this. Although there's a quick way to see how much you've been messed up. Oh, I should mention something. This is what's normally done, although not explicitly. So basically, when you solve an optimization problem, when you know some parameter is varying and you just ignore the variation, you're just doing this. What you can always do at that point is take the x you find here. This problem, the optimal value gives you the optimal value. Gives you a lower bound on the optimal value here. You then take that x and estimate these numbers by Monte Carlo. Okay? And if you find that with the x found from here, when you estimate these numbers by Monte Carlo, this number is not much larger than that, and these numbers are not much larger than that, then you can actually safely presume that you have solved this problem within some reasonable accuracy. By the way, people do that typically informally. That's called a posterior. That's a posterior analysis. That's a standard method in engineering for dealing with uncertainty. Is step 1, ignore it. Step 2, pretend the uncertainty isn't there. Then step 2 is take the design obtained, assuming that all the numbers, the masses, moments of inertia, Young's moduli, all these things, they're all accurate out to full doubles, 12 significant figures. You take that design, and then you subject it to a posterior analysis, which is when you estimate these. Now, if this is 10 times as big as that, then you back off and you go, I had a very nice design, but it's not robust. And it means you're going to have to deal with this somehow head on. Okay. Now, there are lots of variations on this. You can actually put in between the expectation and the function any increasing convex function you like, non-decreasing convex function. That's obvious because if you take a non-decreasing convex function of a convex function, that's convex. And this allows you actually to shape all sorts of things that you might like. So for example, in a constraint, a very common one is to take the expected value of the plus part, non-negative part of this. Now the non-negative part of a constraint is the violation, but it's the amount of violation. So this is the expected violation. By the way, if fi of x omega is less than or equal to some, if that constraint represents something like a resource usage, it means this is the expected overutilization, something like that. If it's it can be all sorts of things. If it is a timing constraint, saying something has to be done by a certain amount, this is called the expected tardiness, right? If your basic inequality said, this job has to be finished by this time, this is the expected tardiness. That works because the plus function is non-decreasing and convex and so on. Now, another one would be this. You could take the expected value of the maximum of all the constraints, and this is the expected worst violation. So that'll work as well. So these are common. These are very common measures here. And I should mention a few others here. But I'm going to mention a few others in just a minute here, which actually should be on this slide. I think I'll add them. But the one that's most obvious is this: a chance constraint. These are called chance constraints, and it looks like this. It's the probability that you satisfy the ith constraint should be bigger than eta. And you're to think of eta as, 95%, 2 nines, 3 nines, this kind of thing. I mean, that's how you'd imagine this. So basically, it would say something like this, optimize this thing for me, but what I want to do is I want the probability that my link goes down or has inadequate signal-to-noise ratio should be, I want the probability that I have inadequate signal-to-noise ratio to be something like 99% or something, at least 99%. And that would be something like, by the way, in lots of contexts, this would be called more specific context, this would be called something like an availability constraint. It basically is, if for example, this represented a communication link having adequate signal to noise ratio or something like that, this would be an availability constraint. It would say that that link has to be available at least 99% of the time. Or it's an outage constraint. You just flip it around. Okay. Now, here's the bad news. Bad news, these are very nice constraints. You can write whole books on them. But generally speaking, they're intractable. And they're not convex. However, you know one case where this is. I don't know if anybody remembers it. What's that? Precisely. So if when f is affine, it's actually bi-affine, and it is affine in x and in omega, then, in other words, it's a linear constraint with uncertain coefficients. That's the most basic one. Then this constraint right here is a second-order cone constraint. And that's actually kind of, when you think of a second-order cone constraint, you should almost think of, when you think of second-order cone programming, you can almost think of it as chance-constrained linear programming, is what it is. So that's one case, but in almost all cases, these are not convex. Now, turns out there's all sorts of good heuristics for doing this anyway. All right, let me ask. Let's talk about a few more things up here. There's actually one more I should add here. How about adding an almost sure constraint? How would you do that? So let me write down what that is. So an almost sure constraint. I have to find the weird little place where anyone can see anything. I guess everyone can see this, more or less. But let me try that. So let's write down this one. Suppose what I want. No, that's not going to work. Suppose what I want is fi. Can I handle that? And is it convex? That's the question. I mean, of course, obviously, in most cases, it's going to be infeasible. I mean, so it's going to have, if your distributions, have infinite or like Gaussian and have, so infinitely bad things can happen with small probability. Constraints like this will just make the problem infeasible instantly. But in some cases, this would make sense. And the question is, can you handle it? Can you use this mechanism? And if so, how? So how do you do that? Can you write that as the expected value of something? What do you think? What would do this? You could write it this way, right? It's just the expected value of the indicator function. Well, here, I f I. So that this is, in fact, less than or equal to 0. Now the indicator function here, this function is the following function. It's 0 if you're negative, and if you're positive, it's plus infinity. That's increasing in concave, increasing in convex. Okay? Everyone agree? I mean, it's rather extreme. It goes from 0 to plus infinity. But the point is, that's increasing in convex. This function is, in fact, if you apply this to f, if you compose this function with f, all that happens is you redefine f to be plus infinity if you violate the constraint. If you say the expected value of that is less than 0, it's pretty much identical to saying that this is true almost surely. So, okay? So you can handle almost sure constraints. And I should mention one more that's kind of widely used. Let me see if I can get it right. I think I can get it right. I shouldn't do this because I'm kind of going off script or whatever, but that's okay. Here it is. A very common version of this is the following: is you take exp of something like that. So that's clearly increasing. Gamma is a parameter, a shape parameter. Exp, of course, goes up very steeply, and so this gives you that's an increasing function. And then you simply put an expected value here. Okay. Now, in fact, you can also do one more thing. That's convex, but then so is that. And I'll just leave it this way. And we'll see why in a minute. So if you do this, and let's just look at the objective for this. Okay. So if you look at this this function here, first of all, let me go over a couple of things of it. I'll just say this briefly because, in fact, it's likely I'm going to make a terrible mistake and regret that I've gone off on this tangent. But anyway, let me try it. Everyone knows that log sum exp is convex and non-decreasing. Okay? This is like a generalization of log sum x, because it's log of expected value of x. Okay? So this is in fact this is a convex function here, okay, of x. Okay. Now the question is, what is it? Oh, and I'm sorry, you put a gamma in front. That's just for the normalization. Actually, you don't need the log, you don't need the gamma, because that's convex right there. This just makes it prettier. So, okay. Now, it turns out when you work out what this is, if you do an expansion on what this is, the first term is actually going to be something like the expected value of f0. That's as if you just minimized expected value of f0. The next term in the expansion of this, I guess this is the not the moment, but the somebody in probability. This is the except it's not the moment. It's the which one? Yeah, it's the there's the moments, and then there's the central moments, or whatever, the centralized ones. This is whatever that. Don't we have? What?
Cumulant?
It is going to be something. All right. Well, let's call it the moment generating function, except that it's not the moment generating function. And maybe it is a cumulant. It's the cumulant generating function. Thank you. Good. Okay. So the first term in this is expected value of f0. The second term is the variance, and that scales with gamma. So when you see this is just a general measure for risk aversion. It's a general construction for handling risk aversion. So let me explain that. Can you make a note, because we'll add this to the. We're going to add this. And by the way, although what I'm going to say now is going to be wrong, possibly wrong, and all that, I don't guarantee any of it. By the time we stick it onto the slides here, it will be correct, or closer anyway. Let me give an example of this. If f0 is a cost that you want to minimize, for example, it's a negative revenue in some finance application. So it's a negative revenue. Then you'd say, well, minimize if you just do nothing here, it's sort of, if you just do the basic thing like this, you're asking, please, maximize my revenue. This is just if you just take the expected value, it says maximize my expected revenue. Okay? But then the variance is irrelevant. So you might actually find some point which maximizes the expected revenue, but has huge variance. And you might care about that. Okay? And you might say, well, no, I want to trade off the expected revenue and the variance as well. You would do something like this, and then gamma is called the risk aversion parameter here. And as you tune gamma, you would trade off expected value versus variance in the first order. So, okay. So that's just, like I said, you can make a whole. We could easily make an entire lecture on it. Easily, you could make a course on it, and there's multiple books on it. Okay. So let's look at how this works with stochastic subgradient. Suppose you have a function that's convex in x for each omega, and I have a subgradient that's g of x and omega. That's a selection of a particular subgradient. It's a subgradient with respect to x of the function f. Little f is going to be the expected value of this thing. You average out over the omegas, and that's going to be convex. Then a subgradient of f is nothing but this. A subgradient is the expected value of that gradient selection function over there. And now comes the interesting part. Suppose you generate m samples from the distribution, and you evaluate capital F of x omega I. Now, if you average capital F of x and omega I, if you just average that's an unbiased estimate of little f of x, right? And in fact, you're going to do this anyway, because you're going to want to estimate this number. So this is something you're going to have to do whether you like it or not, because when you say, here's my number, you want to test what's happening, you want to test your yield or whatever your value is, you're going to actually do this anyway with capital F here. But it says that if at each point you calculate a subgradient and then average the subgradients, then it turns out this thing is actually a noisy, unbiased subgradient. Okay? So by the way, this fits my meta assertion that if you can evaluate a function, you can evaluate a subgradient. And this is an example, by the way, this is an example where technically you cannot evaluate the function, because basically you can't evaluate this exactly except in a handful of silly cases. I mean, they come up and they're used, right? The thing, you know all the things you can, I mean, basically like how many integrals can you calculate exactly. The answer is, 15 or 17 or whatever the number is. But the point is that in general you can't do it, and you're going to have to do this by Monte Carlo. So here's a case where what you can do is by Monte Carlo you can compute this number approximately and as accurately as you like, and at the same time with very little effort other than calling f dot subgrad here or something, get subgrad here, you can actually also calculate an unbiased subgradient. Okay, so let's do an example and see how this works. We're going to minimize the expected value of a piecewise linear function. Now, what's interesting here is that the coefficients ai and bi are going to be random. So I have a piecewise linear function. I want to minimize it, but the expected value, but ai and bi are random, and you're going to commit to an x. I mean, if you want to visualize what goes on here, you commit to an x, and then you will pull random samples of the ai and bi. You'll evaluate this function, and then you'll take the expected value of that, and that's going to be your value. I mean, if the ai and bi are all over the map, it's not that interesting, this thing. If the variation in the ai and bi is in the 8th significant figures, it's also probably not that interesting. It's interesting somewhere where they're in the 10% range, 5% range, 20% range, something like that. That's where the value of sort of being smart, there's actually positive value to being smart. If the variation is just all over the map, there's nothing you can do except, I don't know, take x equals 0 or something like that. If the variation is tiny, you just ignore the uncertainty altogether. Somewhere in the middle, but you can actually do a good job here. Okay. All right. So what we'll do is I'll explain this. We'll do a couple things. We're going to compare this to certainty equivalent. In certainty equivalent, what you do is you simply minimize one piecewise linear function. So that you do by linear programming. You just plug in the expected value of A, expected value of B. This will give you a lower bound on the optimal value here. And here's there's a lot of heuristics you could do, but here's one. One is this. Let's see. We'll plug in the expected value of B, but what's interesting here is when you take the expected value, let's ask about variation in A. Variation in A gets multiplied by X here. By the way, this one, oh no, this does matter because the BIs could have different bounds. Variation in A gets multiplied by X. So here, basically you want smaller X is going to be less sensitive to variation in A. So you just add this, it's a heuristic. There's lots of other heuristics, by the way. Okay, so here's a problem instance. And let's see how these things look. So the AI, those are the row vectors, and then I guess they have, let's see, how wide are they? They're 20 wide. I mean, each AI they're 20 variables. I guess each entry has a standard deviation of square root 5, if we can get this right. B has also very substantial entry. So, sorry. Let me see if I've got this right. That's right. Okay. So AI bar, and then AI bar. Okay, so these are, I think actually these are AI bar here. Should be these, I'm guessing. Although it's probably about the same either way. Okay, so here is the certainty equivalent. Just ignores everything, and you get, let's see, you get where am I? Here we go. So this is the certainty equivalent problem, and then this shows you the distribution of values when you just do Monte Carlo here. So this is Monte Carlo here. So you run and you can see that there's all sorts of values here. All sorts of, these are very unfortunate things where you committed to an X and then the A and the B were wrong for it. This is the heuristic, and you can see that this is the distribution here. This is the heuristic, and you see the heuristic is already doing a lot better. I guess this is the mean. of this. So it's an estimate, well, modulo 100 Monte Carlo samples. That's an estimate of the expected value, of the objective value here. The heuristic is done well because it's penalized large x, and so you've moved away from that or whatever, and you get a tighter distribution here. And then this is f stochastic, and this is computed using the stochastic subgradient, something like that. So this is presumed to be something close to the global optimum. And these dashed lines, I am going to guess the following. They're a mystery, huh? Mysterious ones. We could guess that that's the optimal value. If that is an optimal value of this, then that is a lower bound on this problem. The stochastic subgradient gives you something there, and so if I'm on the stand and if I'm being deposed or there's lawyers present, I could only say something like this. This, again, you have to believe in Monte Carlo, but modulo Monte Carlo, that's an upper bound on the optimal value, and this one here is a lower bound over here. So it's a mystery as to what these are. I'll have to find out what they are. Okay. By the way, if you're doing stochastic optimization, these are the types of, this is how you judge one x or another. You're going to want to run histograms anyway, and so you're going to want to look at things like this. Okay. Oh. So this is 1.34. There we go. Okay. All right. All right. So let's see. If you run if you run a stochastic subgradient for a very long time, this is sort of what happens. You get, I guess, in the theory says it was going to converge to the optimum always. It's just a question of how long it's going to take. And you can see here, in this case, you're taking 100 and you're taking 1,000 Monte Carlo samples to produce the expected subgradient. Actually, in those cases, you can almost argue in these cases that you're actually computing the gradient of the function almost exactly. So these are the gradients. And in fact, this is what sort of the gradient stuff does, goes like that. And it's going to keep going down. And I guess it's estimated to be something like 1.34. And this is how close you get to the optimal value. So that's that. By the way, this is not it depends on here. The effort in each of these is running the Monte Carlos. So in fact, these things, the green one here, for example, costs 1,000 times, is 1,000 times more cost than the other one. So if you actually write these in terms of, if you redo these in terms, if you actually count these things, then you'd find probably that either this one or this one is going to be by far the best one here in terms of, if you rescale the axis, not to be iterations, but actually total number of Monte Carlo simulations. Then actually this one, somewhere in here, is going to end up being the best one. Almost certainly this one here, something like that. So, okay, so that's Monte Carlo estimation. Is that on your current homework? Oh, it's on your next homework. Will be. Homework 4. Good. Okay. All right. Okay. So we'll look at another area where this stuff has been discovered and so on. It's called online learning and adaptive signal processing. So that's something, some of you probably have seen this in some context, like this. So let's see what this is. This is the simplest possible problem. It goes like this. We have x and y. X is a vector and y is a scalar, and they come from some joint distribution. And this, like the simplest possible problem is something like this, is to find a weight vector in Rn for which W transpose X is a good estimator of Y. So that's what you want. Now, these come from a joint distribution. So you don't know, you don't know that, well, we'll talk about that in a minute. So one way to do this is you choose W to minimize the expected value of some convex loss function like this. Now, by the way, if the loss is square, then this is a mean square error, and all you need to know are the second order statistics of X and Y to trivially write out what what the estimator is, right? And it would be linear, and it would be, oh, sorry, actually, in this case, if over all estimators, in fact, the optimal would be linear or affine or something like that. Here. Okay. But for example, if you take the loss to be absolute value, there's going to be no sort of no simple analytic description for this. It's going to depend on the distribution. It's certainly going to depend on more than the second moments of the distribution. Okay, and the simplest context for this is it comes up in adaptive signal processing. What happens? You're given a sample at each time step. That's the right way to do it. So you see, you get a vector x, you get a vector y. That's all, and you want to come up with a vector w. That's all. That's what you want to do. That minimizes some loss function here. Okay. Now, let's see how this works. We'll assume L is differentiable or whatever, or it could, if you take a subgradient. Otherwise, it doesn't matter. If you have a noisy unbiased subgradient, that's a single sample gives you that, because what you do is you take L prime, or actually any GK in the subdifferential of this thing here, and you get L prime multiplied by xk plus 1. So that's a noisy subgradient, and it is a anyway. So the stochastic subgradient algorithm just looks like this, that you step in this step. Now here. You make a step in the negative subgradient direction. Now, if the loss is this is a square function, this gives you the LMS algorithm, which is that you update in the direction proportional to your error. Right. By the way, this is your error at the kth step. That's your prediction error, basically. And you look at your prediction error, and based on your prediction error, you will update your weights. Right. So you don't take a full step here, because in fact these are all stochastic, and even when W is optimal, you will be making mistakes here. So that's why you need this to be damped here. Okay. When this is absolute value, you get something that's called, I guess it goes back into the 70s maybe, is this so-called sine algorithm. And the sine algorithm is very simple. It says calculate the prediction error, calculate the sine of the prediction error, and then bump up or down the component of the weight dependent on the sign. So here, this thing is just a plus minus 1 vector in that case. Okay, so here's just a quick example. You have a problem instance with dimension 10x, and y is a scalar, and these have 0 mean, and they have some covariance. And the expected value of y is, well, the variance of y is 12, so the standard deviation is square root 12, or 3 and a bit. So let's see how this works. And this is just running this algorithm here. And this is with step length 1 over k. And you can see what's happening here. At first, you're making, at least for, 20 by, at first, for the first 10 steps, you're making horrible mistakes. Horrible prediction errors. But after about 50 or maybe 100 steps, you can see that your error has gone down. As to whether or not this has reached statistical equilibrium, I don't know. It might have, maybe not quite, but it looks like it's approaching statistical equilibrium. When this thing converges completely, of course, it's still going to make errors, because even with W star, the optimal W, you will make errors in prediction at each step. So, and that, of course, depends on the joint properties of the joint distribution and so on. Okay. So here's here's the empirical distribution. This is over 1,000 samples. This shows you the distribution error for W star. This is what we presume is the optimal W. And this is what it looks like. So it looks like you can predict it something like this. Remember that Y itself varies over, has a standard deviation about 3.5. So this maybe has a standard deviation of, I don't know, whatever, a half or something like that. So the point is, you can actually predict it within about 15% is the way, this is when you have the optimal weights. You're predicting it about 15%. You cannot do any better. That's what it means to be W star. Okay. So I think this finishes up this. Actually, you will see some of this on your next on your next homework. So, any questions about this or? Okay. I should mention we're going over this kind of fast, obviously, in lecture. So there are notes on this. They flesh these things out in a little bit more details, and of course, there's homework on it. So, I mean, not a big deal, but just one, so you can say you've solved the stochastic optimization problem or something. If anyone asks you. By the way, my suspicion is that a lot of people who've even written long books about it haven't actually really done it, so you'll be ahead of them on that. So that might be an exaggeration, but not much of one. Okay. We're going to start a new section of the class, which is on methods that are in spirit like subgradient methods. They require only subgradients, absolutely nothing more than subgradients. But they are more efficient. Certainly, in theory, some of these methods are actually efficient. So we'll see that. We'll get to some methods that are actually just, according to the theory, they're efficient. They're polynomial time and all that. They're quite slow, but they have uses. Some of them actually work quite well. We'll get to some of those. And they're all based on the idea of localization and cutting planes. And actually, they're beautiful. Just the ideas are beautiful. They have lots of applications in distributed optimization, distributed design, and it's good to know about these things. Okay, so what is the idea in a localization method? In a localization method, what happens is, you know what these are? Let me explain it. These are basically generalizations of bisection in R. So bisection in R, how does that work? Well, it works like this. You have an interval, and you know the solution is in this interval. So you maintain an L and a U. This is bisection. Then you do something like you check the middle, right? And then by analyzing something in the middle, like the derivative or something like that, what you know is now, after you know that, you say that actually the solution is either on the left or the right, right? This is the essential idea of bisection. And so at the next step, you have a new interval, which is exactly half the size of the interval before. So everybody knows that's bisection. We all know about that. Okay. Now the cool thing about bisection is that your ignorance, as measured by the width of the interval, goes down exactly by a factor of 2 at each step. Or, if people who are actually trained in information theory allow me to say this, you get 1 bit of ignorance reduction per step, right? Because at each step, the width of your ignorance as to where the solution is goes down exactly by a factor of 2. So you gain exactly 1 bit of information about the location of the optimum. Okay. Now this is bisection. Okay. Then you might ask yourself, maybe you have already, is there an analog of bisection in R2 or in Rn? I don't know if you ever thought about this. Have you thought about this? And it's complicated. It's very complicated. And you could easily convince yourself the answer is no. And the reason would go something like this, that R, unlike R2, R3, and so on, is ordered. It's the only one that's ordered. So you might say you can only bisect. That's a very special thing. It only happens in 1 dimension because it's ordered. Actually, what you're going to see in the next couple of lectures is that's false. You can actually do bisection in Rn. It's not going to look exactly like bisection, and it's not going to be as good. You're not going to get a full bit at each step, but you're going to get something like it. You're going to get a guaranteed minimum fraction of a bit. And it's going to be more complicated because instead of an interval localizing your solution, it's going to be some general set. So that's the super big picture. This is going to be bisection in Rn, which is actually, if you think about it, pretty cool. Okay, so, all right. So and the way it's going to work is this. So localizing is that you're going to maintain a data structure of some kind or some set, and and it's going to summarize what you know, and it's going to say something like this: my solution is in that set. Exactly like in bisection, we have an interval, and you say, if you stop bisection early, you terminate it, and you say, what do you know? You have an L and you have a U, and the optimal X star is between L and U. U minus L is a measure of is a numerical measure of your ignorance as to what X star is, and so on. Okay, this will be the same thing, except it's not the data structure or set is not going to be an interval. That's for sure. These methods only require a subgradient of the objective or constraint function at each step. So they're going to require, again, these are going to require only a weak subgradient calculus. So if you implement methods to calculate, if you implement methods that calculate a subgradient, that's fine. Anything you could use for a subgradient method, you could use for a localization method. And that means that they directly handle non-differentiable convex. They'll also do quasi-convex problems. Now, these are actually going to require more memory and computation per step than subgradient methods. Subgradient methods require nothing. They basically, they call a subgradient, and then in fact, how many of you know about like BLAS and BLAS and things like that? That's too few. Now, I know it's early, but okay, few more coming. Okay, a handful of, okay. So basically, what's the computational effort in the subgradient method? Oh, we never really talked about it. It's going to be a very short conversation, so let's do it. What's the computational effort in the subgradient method? What do you have to do at each step? You have to get a subgradient. Okay, and then what do you have to do? What computations do you have to do?
Scalar vector product and then add two vectors.
Yeah, good. Okay. How do you say that in BLAS?
AXP.
Yeah, it's AXP. It's DAXP, I guess, but it depends what you want to do. So, in other words, it's about the most pathetically small amount of it's an order n update. N, by the way, is the number of variables. So if you merely that means basically it's the effort of just sort of writing to the variables and so on. So it's nothing. Just accessing the variables, doing 1 or 2 flops per variable. That's all. So okay. So a good approximation of the computational effort per step of the subgradient method is nothing. All the effort is in calculating a subgradient, and the other one will be free. Okay. Okay. So these are going to require more. We're going to actually have real calculations here. Now these can be much more efficient in theory for some of them, and in practice for some, and they don't completely coincide. So we'll see ones that are good, that are efficient in theory but not practice. We'll see. No, that's not true. Well, all the ones that actually work well in practice, actually, I'm pretty sure are also efficient in theory. But but the sets are not going to be the same. Okay, so it's all based on the following idea. You have an oracle, and it's actually better to well, one way to do this is to abstract this away from subgradients. Subgradients will come in later. But you have an oracle, and the oracle is going to go like this. So what we're going to do is we just want to find a point in a convex set, or determine that the set's empty. And the only access to X is going to be through a cutting plane oracle. And what's a cutting plane oracle? It's going to be something, it's going to go like this. You're going to query or call the cutting plane oracle at a point X. And what's going to come back is either a token or something that tells you you're in the target set, in which case, by the way, you're done, right? Or it's going to come back and give you a separating hyperplane between little x and big X. This is called actually a cutting plane, or a cut, since it eliminates a whole half space of x's from consideration. So let me show you what this looks like. Well, actually, let me just draw a picture just to show you what this how this works, or what it looks like, because that's in fact, this one you have to draw pictures for everything. Okay, so the way it works is this. There's some set here. We don't know this set. This is known only to so we don't have access to this set. This is X, capital X. And then what happens is all you can do is actually query an oracle at a point. So if you query an oracle at this point, the oracle simply returns a token that says you're done, or it's in it. However, if you query the oracle here, the oracle has to do the following. It has to return a cutting plane, and a cutting plane is anything that separates that point from this set. that's a cutting plane. So, and the idea is basically, when you know that, what you know is that this entire half space cannot contain any point in here. And therefore, there is no reason to look in this half space anymore. When you get this half space, the exact semantics is this. By the way, it does not tell you that this set could be empty. In which case, by the way, you're allowed to return the semantics, the agreement there, to actually conform to the semantics. If the set capital X is empty, you can return any cutting plane you like. Because it is true that there is no point in here that is also in your set. Because actually there's no point in your set. Okay? So that's how this works. Okay, so this is the idea. And by the way, this is something like bisection. Because in bisection, what happens is you query at a point on the line. This is bisection. And in fact, what bisection tells you says either the solution is there or there. It actually returns, that's a cutting plane. And cutting planes in R are a little bit boring. They're basically they're sort of a point saying it's either to the left or to the right or something like that of some specific point. So that's a cutting plane. And if you want to think in your head that this is something like you're getting one bit of information, which is not quite right, you're welcome to, because it kind of gives you the idea. Now there's an idea of a neutral, and oh, by the way, you can actually, if this is the point you query at, you can actually return lots of cutting planes. Obviously, any plane, there's tons of planes that fit in between this point and this set. Any one of them is an absolutely valid cutting plane to be returned. Okay? So, I mean, you could return this, for example. That would be fine. You could return something like this. I mean, it just doesn't, it doesn't matter. By the way, if this cutting plane goes through the point, the query point, then it's called a neutral cutting plane. So it's called a neutral cutting plane, and that looks like this. So here is your point X where you query, and what comes back is a neutral cutting plane. So it basically says, do not look to the right here. That if this set even if it's even non-empty, it's entirely contained on the left here. So all of these, a neutral cutting plane goes through that point like this. Okay. A deep cut is one where you actually slice off, actually not just X, but like a little ball around X is what it means. So it basically means not only is your point not optimal, but in fact it makes a little ball around it and says it's not optimal too. Because if this is deep, it says that there's a little ball here that is not optimal, sorry, not in capital X. That's it. By the way, there's also an idea of a shallow cut. A shallow cut is one where you get something over here. It's not really a cut. Those come up too. So, although we won't look at them. So, okay. So let's do unconstrained minimization. So here's the way. Let's do this. We want to minimize a convex function. We'll let capital X be the set of optimal points, just so any minimizer. And what we're going to do is this. We take the basic inequality for a subgradient. Then that says, of course, that if you evaluate a subgradient at X, you get a cut. You get a cutting plane. And that's actually sort of the point, is that if you evaluate a subgradient, you immediately get a neutral cutting plane at that point. Okay. So, and basically the way that works is this: you have the sublevel sets. Let me draw a function here. So here's some non-differentiable function. We query at this point here, and you get a subgradient. Looks like that. There's many subgradients, but they all give you a cutting plane for the minimizer. Because when you get a subgradient, what you're told is that for this entire half space defined by the subgradient, passing through that point, this half space, there's no reason to look anywhere here, because every point here has a function value larger than or equal to the function value there. So there's no reason ever to look there, because you'll only find worse points than this one. Okay, so that's a neutral cutting plane. Actually, the fact is you can also get this is the picture which I just drew anyway. Looks like this. So Basically, what you should think of is this. So when you evaluate a subgradient, you're actually getting a cutting plane with respect to what the solution is. Okay? Now, you can actually get a deep cut. And a deep cut goes like this. It's much more interesting. It goes like this. Suppose you know a number, f bar, that is bigger than f star, but lower than your current than the current value. And for one common choice of f bar here is actually the following. Is f bar can be the best point found so far. So it's what we called before f best k. Okay? And there's no reason, if the last point was your best point, then of course these are equal and none of this holds. But if the current point is worse than the best point you found so far, it means actually it tells you that your current value is bigger than that, and then this says that if f of z is bigger than f of x plus this thing, you must have this. If this holds, then you have f of z is bigger than f bar, which is bigger than f star, and that says that you're not in the optimal. Then you're not in the optimal point. Okay, so you have a deep cut, and the deep cut is this, right? So and there's lots of other examples of this. If you knew f star, for example, that would be another example. You just put f star right here, and you get a deep cut immediately. You get a deep cut. So that's a deep cut. Okay. In a feasibility problem, you'll take x to be the set of feasible points, and if x is not feasible, so here's how you generate a cutting plane. Someone gives you x, you cycle through all the fi's. If all of them are less than or equal to 0, you have to return the token a short token saying done. X is in big capital X. If not, it means that one of these fails. So in fact, you could even stop at the first one will generate a cutting plane. So the first time you get a violation, what you do is you evaluate a subgradient, and you get here you can actually do a deep cut, and this gives you a deep cut. Right, so that gives you a deep cut. Here's the deep cut, is right there. So that's how this works. So the idea is if you want to solve a feasibility problem, you cycle through the constraint functions. If you get to the end of the list, everybody's satisfied, done, you're feasible, it's all over. Otherwise, you take any violated constraint. First one you encounter, for example, call get subgradient on it, and return a deep cut plane at that point. Okay? Okay. And if you have an inequality constraint problem, here's how. So actually, what I'm doing now is I'm explaining how to create a cutting plane oracle, how to wrap an oracle method around various problems like feasibility, unconstrained optimization, constrained optimization, and so on. So that's what we're doing here. How do you do an inequality constraint problem? That's easy. If x is not feasible, then you get a feasibility deep cut, and what you do is if someone gives you an x, you cycle through all the constraints. If you reach the end of the list, you set a flag saying that x is feasible, and you evaluate f0. By the way, when you evaluate f0, you possibly will update the best value found so far, best feasible value found so far, right? However, if you don't make it through your list of constraints, you stop at the first violated constraint here. You get a subgradient for the violated constraint, and you return this deep cut here. And this deep cut is very simple. You could actually not only return the deep cut, but return an annotation or a comment to the caller, to the oracle caller. Although it's not required, the semantics doesn't require you to give a comment back. You can give a comment, which is basically like, here's a deep cut. And if someone asks you, why is that a deep cut? You could say, well, because anybody who doesn't satisfy this inequality here, I guarantee is going to violate the 13th constraint. That's what it means. By the way, you're not required to do this, right? But you could do this. Okay. Now, if all of these are correct, if x is feasible, you just have a neutral objective cut, or a deep cut if you have an objective value like that that's known. Okay? So now you know how to generate a cutting plane oracle for pretty much any problem you would encounter. Constraints, inequality constraints, all those sorts of things. And now I can give you a completely generic localization method. It goes like this. It's conceptual because that means something in here is vague. I'll get to that. It works like this. You start with an initial polyhedron known to contain X. Okay? Or it doesn't have to be a polyhedron. It could just as well, it could be any convex set known to contain, it could be a ball or something like that, known to contain the initial point. Okay? Sorry, the whatever, to contain this, which is no guarantee that this is not empty. Okay? Then it works like this. You choose a point inside this polyhedron. Now, this part is vague, and we're going to get to that in great detail. So you choose a point in this polyhedron, and you call the oracle at that point. If the oracle returns, says that you're in, returns the token, the success token, done. Whole algorithm's over, you're done. If it doesn't, it has to add a new, it has to return a cutting plane, and you simply update your polyhedron. So the idea of the polyhedron is it summarizes what you know at each point. Or another way to say it is, if you want to think of it from the negative point of view, it summarizes your ignorance, is what the polyhedron is. Because basically, the true semantics is this. PK at step K or whatever is something like, it's the set, that's all you can really say about where capital X is. You'd say, if X, all I can say is X, capital X is a subset of PK, nothing else. Now, if that's empty, you can certainly quit, and then you can certainly say the problem is infeasible. And you said K equals K plus 1, and go into that. So here's the picture. And the picture is drawn here for a neutral cut. So here's the way it works. PK is, and by the way, this is nothing but a generalization of bisection. In bisection, you have a polyhedron in R. Polyhedra in R, we can have a very short discussion of the theory of polyhedra in R. Polyhedra in R are intervals. Okay, so it's not that interesting. Okay, so here you have a polyhedron. You query at this point here, and a neutral, in this case, a neutral cutting plane comes back, and it says that it points in this direction, and that says you have just ruled out all of this stuff here. This is impossible, and so that's your old set of where capital X might be if it exists. That's your new set. Oh, and in fact, you could talk about all sorts of measures, but a very good measure would be, and absolutely defensible, I think, in information theory, would be something like this. The log of the volume of PK is a very good measure. If it's log base 2, it's a very good measure of sort of the actual number of bits of information you gained here. And so actually I'm going to ask you, for this particular iteration that went from this to this, how many bits of information did we obtain? Our ignorance went down by a certain number of bits. What's the number? 12? 0.1? What is it? Just eyeball. Yeah. If it was 1 bit, it means that the volume went down by a factor of 2. Or the area, it's the area. Does the area look like it went down by a factor of 2? What? More than 2. Did it go down by a factor of 4? No, probably not. So 1.5 was a perfectly good estimate. So our ignorance just went down 1.5 bits, roughly here, okay? Now actually, let me ask something for this problem. What's really interesting about this now is when we queried at this point, we had no control over what cutting plane was going to come back. And so let's actually draw some pictures about what's the best thing that could have happened. What's the well, let's think about that. So I don't have to have the same set, but here it is. Okay, so there it is, and I query at this point. And let's do first let's do deep cuts. All right, so I query the oracle here, and what would be like the best thing that could possibly happen with a deep cut? My lucky day, I have tipped or bribed the oracle, And what happens? Yeah. So the oracle comes back saying if there are any feasible points or any points in capital X, they've got to be, I guess it points that way. That's our protocol. It's that way. So basically, it eliminates all of this and leaves only, quite conveniently, this one vertex. Right? This could happen, okay? At which point, by the way, if it's really literally just that single point there, we can now say, with certainty, we're done. Oh, well, I'm sorry, I have to call the oracle at that one point and then have it return to me the token saying you're in. Right? So that's that's it. So this is the best thing that could happen. And in fact, let's suppose it wasn't quite that good, but it left a little tiny baby triangle here. If there's a little, but in this case, what's our ratio of what's our ignorance reduction ratio? In this case, it's huge, absolutely huge, right? I mean, it went down by some. I mean, I guess if it went from the whole thing to a point, then our ignorance reduction ratio was infinite, because we went from something with some area to zero area, right? So that was it. But if it went down, so arbitrarily good things can happen. Okay. Well, it's silly to base an algorithm on that. Not only silly, but it won't work. So let's talk about what's the worst thing that could possibly happen. Well, the worst thing that could happen is that you're going to get a neutral cut. And then let's talk about the direction of the neutral cut. If the direction of the neutral cut, in this case, looked like that, how many bits did you get? Just eyeball it. What? 2, 3, something like that. You got a couple of bits. You were lucky, right? Because you're getting a full 2 bits. By the way, this is sort of like you're now beating bisection, right? In bisection, if you query at the middle and you go down by a factor of 2, you get exactly 1 bit per iteration. In ignorance reduction, you get 1 bit. Here, you were lucky. But suppose, in fact, it came back like that. So your prior knowledge, although really probably the correct name for this thing is your prior ignorance. Your prior ignorance is this polyhedron here, and your posterior is this thing with this part cut off. And so what's your ignorance reduction now? Yeah, way under a bit, right? So in fact, if you think that this is like, I don't know, 1/8 the size of that, or I don't know, 1/6 or something, so it's between 2 and 3 bits, then it basically says the area went down only by 1/7/8. It's a factor of 7/8, and so you did quite poorly.
You gain nothing if your cut doesn't go through the polyhedron?
No, you're always going to gain something. That you're guaranteed. Yeah. Oh, well, no, hang on. Let's look at some query points. Let's now discuss query points. Okay. So let me ask you this. Suppose I query here. What can't happen if you query there? It can't come back and say, oh, you got it. I mean, otherwise something is wrong, right? Because basically, according to all the contract, I'm supposed to be able to certify that any point that's actually in capital X is in this polyhedron, and I called the oracle there and it said, yep, that's it. So something is wrong. Okay. However, could something good happen calling here? Could I call the oracle there and have something good happen? Yeah, absolutely. So what could come back could be this plane here. In which case I say, great, I win. I got it in one step. Okay. However, bad things could happen, and I'll show you one of them. You could simply call at this point and get this thing back, and how much ignorance have you reduced now? None. So, okay. So, all right. So basically, querying outside is at least in the worst case as dumb as you can get, right? Because then if you query outside the localization region, there's a chance that your ignorance won't go down at all. Okay. So, how about querying here? And let's do neutral cuts. If you query there, by the way, if you're lucky, what's going to happen? Neutral cut through that point. What happens? It's going to go way down. What's going to happen is it's your lucky day. You point in that direction. You have a huge reduction in ignorance, right? Okay. On the other hand, it could just as well have worked this way. And if it worked that way, your reduction in ignorance, though positive, is extremely small. Okay. So now you begin to think, if you wanted to do something that's going to work well, even in the worst case, you obviously want to query this somewhere near the center. I mean, that's clear. And in fact, what you'd really like would be this. You'd really like to have a point where no matter how a plane goes through that point, the area is divided. In fact, if you could find a point in that polyhedron where no matter every hyperplane that passes through that point divides the area 50-50, that would be perfect. Because then, at each step, your ignorance goes down by exactly 50%. Everybody following this? That would be the exact analog of bisection. Because in bisection, your polyhedron is an interval. You query at the middle, and it's either the posterior polyhedron is either the left or the right half. Your ignorance goes down by exactly 1 bit. So that's it. Now the question is there a point in a polyhedron for which any plane passing through it divides the polyhedron 50-50 in volume? And the answer is, sadly, no. There's no such point. So, although that was a great idea, it's not going to work. Okay, so that's not going to work. So, we're going to see, though, there's points that are almost as good. That's the wild part, as that. So, it's not going to be as clean as that. If it were that clean, it would be actually quite cool. But sadly, it's not the case. Okay, so all of this is the argument for why we would want to pick this near the center, and that's because we're risk averse. By the way, if you want to make an algorithm that's risk seeking, go ahead and evaluate it near the boundary. I mean, go ahead if you're going to trust it. If you're going to make a if you're just punting at that point, go ahead and query it outside and tip or bribe the oracle or something. But okay, all right. So here's just a picture of how this would update typically. So here's PK. Here's this point. This shaded part has been ruled out. Let me see. Sorry. Part. I've got it now. This is showing if that's your point. If you choose to query here, this is what happens. The left column shows maybe good things, and the right column shows bad things. And in this case, your ignorance reduction is, it's about 1 bit in each case. And in this case, it's considerably more than a bit and considerably less than a bit here. Okay. Okay, so we've talked about this already. Very famous example, the most famous example by far of a localization method is bisection on R. PK is an interval. Obvious choice for the query point is the midpoint, and your ignorance goes down exactly by a factor of 2 at each step. So that's the bisection algorithm. It's totally obvious, but it's a member of this family of cutting plane methods. So that's it. And in fact, you can say all sorts of things. So the uncertainties so you get exactly 1 bit. We've already said that. The number of steps required to get an uncertainty in x less than r is this. It's log 2 of the length of P0 divided by r, and that's log 2 of the initial uncertainty divided by the final uncertainty. So that's the number of steps you're going to require. That's exactly the number of steps required. So that's what it's going to be. Okay. Now we're going to talk about specific ones. The main difference in all cutting plane methods is how do you choose that point xk. And so we'll get to look at least at one. So here are some methods. One is the center of gravity method. Another is the maximum volume ellipsoid cutting plane method, Chebyshev center, analytic center. And we'll go over all of these, and we'll go over this one in some detail because this one actually has the interesting attribute of actually working extremely well in practice. We'll get to this one. This is a beautiful one. It's the most beautiful one by far, and it has one minor drawback that we'll get to today. And then these actually also, this one at least works well as well. So, okay. So here's a CG algorithm. It goes like this. You want to query in the center of your polyhedron. So we're going to take the CG of that polyhedron, and that's the integral of x divided by the integral of 1 over that thing. And then it turns out there's a basic fact. It's actually quite extraordinary. It's not hard. We should put it possibly on the homework because it's a guided proof. It's very short. It goes like this. It's totally wild. It says basically if you take any polyhedron in any dimension and you take the center of gravity of it and you put a hyperplane going through that point, you divide your polyhedron into two regions. And the question is, how unevenly can that divide the volume? Is it Rn? And the answer is, it can never be worse than 6337. Period. Ever. Isn't that insane? Notice it has nothing to do. Oh, and by the way, it's actually you can sharpen this for dimension. Well, for dimension 1, actually, this is 0.5 because it's the center, right? For dimension 2, there's another number which is actually bigger, smaller than 0.63. But quickly, for n equals the actual bound that you get, by the time n is like 4 or 5, it's very close to this number. 1 minus 1 over e. So totally insane result. It's very cool. So it says we can't get 1 bit, but we can get something like log. You can get log base 2 of 1 over 0.63 bits, which is not a bit, but it's close. It's like a bit and some change, it's a little bit less than a bit. You get like 0.8 bits or something in any dimension. It's completely insane. So this algorithm is from 1963 or something like that. This one was actually found both in Moscow and actually in New Jersey as well. But it's one of those rare things. So, okay. So now let's see how the CG algorithm, and I'll give you just the complete proof of convergence right now. So it's simple. It goes like this. Suppose P0 lies in a ball of radius r, but x includes a ball of radius little r. Okay? So, and you can take x to be something like the set of epsilon suboptimal points in your other problem, but it's general. Then, then it says suppose a bunch of points are not in capital X, and that means that the polyhedron here still covers capital X. Then that says the following. It says that the volume of the kth polyhedron. First of all, it says that little x is bigger than that ball of radius r, and so it has a volume that's at least alpha n r to the n, where alpha n is the volume of the unit ball in Rn. Right? There's some formula for that, but it's not going to matter to us. That's volume of pk. That's less than this because each time you run the CG algorithm, each step, your volume goes down by at least a factor of 0.63. That's the worst thing that can possibly happen to you. And so it's 0.63 to the k times the volume of P0. But this thing is less than the 0.63 propagates forward. This is less than or equal to alpha n capital R to the n because P0 is inside a ball of radius capital R. So you get this. It's really this stupid. You cancel the alphas and you divide, and you find that k can be no bigger than 1.51 n log 2 capital R over R. It's super cool. Now, bisection works like this. In R, there was no 1.5 here, and n was gone. So that was the difference here. So this is kind of like bisection on R, except that you're not making a full 1 bit of progress. You're actually making, I guess we could work out what it is. By the way, notice that log base 2, actually n, this thing is actually the ratio of it's the number of bits you required to go from your initial to your final ignorance level. So the advantages are, well, it works, it's affine invariant, number of steps proportional to dimension n, and log of uncertainty reduction. And the disadvantage is this. It turns out that finding the center of gravity of a polyhedron in Rn is exceedingly difficult, far harder than solving any convex problem. And this is the sad news. And generally speaking, it is considered a substantial disadvantage when one of the subroutines called in an algorithm has a complexity far higher than the original problem you're trying to. That's generally considered a disadvantage. Now, we're going to quit here, but I'll say that there are actually some very cool methods. This can be made to work by computing an approximate CG. By the way, if anyone's interested in that, there's some very cool projects that can be done on that. And we'll quit here.